Hello, this is Zhuo Biaoqiao. I'm honored to be here on this presentation. Today my topic is application of various CNN in the field of target classification and detection. I'll show it in the order of these 5 parts. Let's begin with the introduction. At present, CNN has developed rapidly in terms of structure and has widely applied in industry such as retina detection, gesture recognition, and multi-object detection. CNN has also expanded many structures such as ResNet, EfficientNet, and faster RCN. The research aims to explore and verify the applications of these novel structures in various fields. I use two projects to illustrate the performance of CN. One is diabetic retinopathy detection. It's a Kaggle competition. The other one is the road object detection. The first project originated from a Kaggle competition. It's 2019 aptos detection. At present, doctors are responsible for diagnosing ocular fundus lesions caused by diabetes. The pathogenesis is that ocular thrombosis caused by high sugar seeking concentration promotes secondary growth of blood vessels in the eye. Vitreous gel can cause blindness. Generally, it can not be detected and treated in time due to various factors, resulting damage to the retina and ultimately blindness. The top-ranked programs in this competition mostly use model ensemble methods to solve the problem. So the solution I chose is to use the EfficientNet baseline model for model ensemble. This program finally obtained the same score trade and as a competition, thus verifying the effectiveness of the model. The goal of the second project is to build a classifier that can detect road targets. The classification task cares about the whole, and it gives a description of the content of the whole picture, while the detection focuses on a specific object and requires that category information and location information of this target be obtained at the same time. Compared with classification, detection gives an understanding of the foreground and background of the picture. We need to separate the target of interest from the background and determine the description of this target. Therefore, the output of the detection model is a list. Each item of the list uses a data group to give the type and position of the detected target. In this regard, we use the FastR CNN network architecture to model and use it for road testing. The test results show that it has a good recognition performance. Next, we mainly explain the model we used, which is divided into two parts. One is EfficientNet, and the other one is faster RCN. In order to clarify the structure of those two neural networks, each needs to introduce some pre-networks. We know that traditional convolution neural network, which requires a large amount of memory and computation, so it cannot run on mobile devices and embedded devices. Therefore, the Google team proposed the MobileNet network in 2017, which is a lightweight CN network focused on mobile or embedded devices. Compared with the traditional convolution neural network, the model parameters and the amount of calculation are greatly reduced under the premise of the small decrease in accuracy. The highlights in the network contains two facts. One is dipwise convolution. It can greatly reduce the amount of calculations and the number of the parameters. Second is the set of the hyperparameters, alpha and beta. They are, they are artificial sighting, different from traditional convolution. Each convolution kernel depth of DW convolution, that is the channel, it's unique, unlike the traditional convolution. The depth is equal to the depth of the feature map. Each convolution kernel is only responsible for performing operations with a channel of the input feature map to obtain a channel of output feature map. And therefore, the number of convolution kernels is the same as the depth of the input. Furthermore, the output feature map is also the same as the former. It will reduce the amount of parameter calculations. Usually, DW convolution needs to be combined with PW convolution to form DW separable convolution. Pointwise convolution is just a traditional convolution layer with kernel size equal to 1. So its channel is equal to the input channel. In theory, the calculation amount of the ordinary convolution is 8 to 9 times uh, faster than that of the DW and DW plus PW. I've listed the process of calculation. We ignore the concrete network and go straight to the version 2 model. It's smaller with higher accuracy. It has two highlights: inverted residuals block and linear bottlenecks. It's an inverted residual block because compared with the residual block in Resonite, it has the opposite operation before and after 3 times 3 convolution. Besides, it uses ReLU 6 function rather than ReLU function in activation phase. So it's just like a bottlenecks. Here's the structure of inverted residual block. When stride equals to 1 and the input feature map has the same shape as the output feature map, there is a shortcut connection between input and add. Here's the concrete parameter of the MobileNet version 2. I show it in detail without explanation. More comparison with other models can be seen from paper I listed. Then they proposed version 3. It has 3 updates. We pay more attention to 1 and 3. Compared with version 2, version 3 is not much different except for the addition of the SE module, which is the attention mechanism. Here shows a simple simulation of the SE model. The idea is simple. For the obtained feature map, perform a global average pooling operation on each channel to obtain a one-dimensional vector with the same number as the channel. Next, we obtain the output vector through 2 fully connected layers. The number of fully connected layers in the first layer is a quarter of the feature map channel. The number of nodes in the second fully connected layers is consisted with the feature map channel. It's just equal to the feature map channel. The output vector represents the weight of each feature map channel. As for activation, each layer uses different activation function, simple denoted by nonlinear. 1 times 1 layer do not use a function. The reason to use hard switch function rather than switch function is that compared with it, hard switch has an excellent simulation for switch with lower calculation in computation. Uh, in MobileNet version 3, they use hard sigmoid to replace sigmoid function and replace switch with hard switch, which can reduce calculation. Besides, they also optimize the structure of last stage for faster inference without losing accuracy. Here's a MobileNet version 3 large structure. Uh, it also has a small structure. Uh, I've illustrated each part of the whole network. Now I can introduce the network I used in Kaggle computation. EfficientNet is a model proposed by Google in 2019 by simultaneously exploring the impact of the input resolution, network width, and depth on model accuracy, combined with a series of standard model structures obtained from engineering experience. Uh, EfficientNet has fewer parameters than mainstream models, and its accuracy rate is also high. You can see that the B7 model reached the highest accuracy rate of 84.7 percentage on the ImageNet at that time, and also had a fewer parameter. How to increase the width, depth, and input resolution of the network at the same time? EfficientNet is obtained by Google through network architecture search technology we call NAS. I don't need to illustrate because we just use the network. In short, we can now understand the structure of EfficientNet. The parameter of the EfficientNet B0 model are shown here. The stage is divided into 9 stages. Stage 1 is a 3 times 3 convolution layer. Stage 2 to 8 is a convolution block in MobileNet. And the stage 9 is a 1 times 1 convolution layer after pooling. The final feature resolution obtained by connection is the height and width of the feature map input to each stage. The channel corresponds to the number of feature map outputs by each stage. The layers indicates how many times the operator is repeated. The stride can be inferred from the resolution information. Uh, it only corresponds to the stride of the first operator of each stage, and the remaining stride is 1 by default. The mobile convolution is just the same as the mobile convolution layer in the MobileNet. Here shows a clear view on mobile convolution. Note that in the implementation, only those which has a shortcut connection uses a dropout layer. You can go back to the part of the MobileNet version 3 to check the detail. For SE module, it has some difference with that of the MobileNet version 3. The number of nodes in the first fully connected layer is a quarter of the channel of the input MB convolution feature map, rather than a quarter of the current feature map, and use the switch activation function. The number of nodes in the second fully connected layer is equal to the feature map channels output by the dipwise convolution layer, and the sigmoid activation function is needed. Next, we observe how the the other model parameters are set. For the B3 model, its input image resolution is 300 times 300. The Y coefficient represents the magnification factor in the channel dimension. For example, the number of convolution kernels used in 3 times 3 convolution layers of the stage 1 in efficient night B0 is 32. Then in B3 is 32 times 1.2 is equal to 38.4. And then round to the nearest integer multiple of 8, which is 40. The same for other stages. Depth coefficient represents magnification factor in depth dimension. It's only for stage 2 to stage 8. For example, in efficient night B0, stage 7 has L equals 4. We can see from here. Then in B3, it is 4 times 1.4 is equal to 5.6, and then round up to 6. Same for other stages. For Kaggle computation, we use EfficientNet B3, B4, and B5 to generate 15 baseline models. Next, I'll illustrate how to construct our model. For dataset, I use two models. They are aptos dataset, which are provided by the Kaggle. It has training set and testing set. The number of the training set and testing set are listed here. It also has some hidden data for privately testing. Our goal is to obtain the private score as high as possible. Then we need an IPAX dataset. It's also listed here. I use it for training. The reason to choose it is that it has the same distribution of the same labels. For pre-processing, we need to execute the Gaussian blur and the central crop operation to make it clear enough for transfer learning. It conforms to the natural law of the case observation, and the health funders is close to half. Figure elaborates the whole modeling methods. First of all, the Apex dataset has provided a central cropped version, which is used as a training set. The raw aptos dataset is used as a validation set, and the EfficientNet series model is used for pre-training, so as to obtain 3 pre-trained models, B3, B4, and B5 in stage 1, which called a series model. Then we need to use pre-processed picture of the aptos dataset for transfer learning. Obligatorily, the same pre-processing operation must be performed on test dataset to make predictions when predicting the private datasets later. In principle, highlight details obtained after operation facilitate the classifier to distinguish tiny blood vessel. Intuitively, such funders' photos looks more like the moon. Constructively, for the purpose of verifying the accuracy of single transfer learning model, we can classify the aptos training set before pre-training with 80% as a training set and 20% as a validation set. Before training the transfer learning model, We also need to perform five-fold stratified sampling on the aptos training set so as to train five prediction model for each series of the model, a total of 15 models. Next, we load five models of the same series. Uh, for example, we load five models of B3 to predict the aptos test set and get the logits value in the range of 0 to 4. We will take the average logits value obtained by each series of the model and train the three average logits values and the true value using catboost, xgboost, and svr to obtain the final classifier. The logits value is just a feature map. Consequently, the whole model are divided into three stages. In stage 1, the picture is predicted by 50 prediction model to obtain the largest value, we say feature map. And in stage 2, the average largest value of the model calculated and then put into three classifiers. Eventually, the model bagging is performed using a simple maximum voting methods. In this research, we used quadratic weighted coherence uh, kappa score as our main metric. Kappa score measures the agreement between two ratings. The quadratic weighted kappa is calculated between scores assigned by human raters and the predicted scores. This metric varies from -1 to 1. -1 denotes complete disagreement between raters, and 1 complement denotes complement agree between raters. The main reason to use the kappa ratio is that we do not have access to labels of validation and the test datasets. Kappa value for those datasets is obtained by submitting our model and runner's code to checking system on Kaggle site. Moreover, we do not have explicit access to image from the test dataset. Along with kappa score, we calculate weighted F1 score, accuracy, precision, and recall on holdout dataset of 333 images taken from aptos 2019 training data. Final score on private dataset have reached 0.9137, a little bit lower than the original result. The original game's public score is also as low as mine, so let's ignore this bad score. Now I'll show the code for you.